corollary of our formula, our theorem just stated, we have this result. If B is the closed unit ball in Rn, and then there is no map from there is no C2 map. There is no C2 map that is twice differentiable phi from B to B such that phi B contained in the boundary of B, and phi is the restriction of phi or phi x equal to x for x in the boundary. Okay, so we have this important corollary. As we see before, this corollary implies that the C2 version of the twice differentiable version of the Brouwer fixed point theorem is true. From this corollary, you can obtain the Brouwer fixed point theorem for smooth maps. Okay, therefore, this is a very important consequence of this theorem. The change of variable formula only require once the domain omega is good enough, we only require the change of variable map to be to carry a parametrization of the boundary of omega to the boundary of D. Okay, phi need not to be one-to-one between omega and D. It can map several different points in omega into a single point in D. This is allowed. Okay, now let's have a look. Before proving our theorem, let's have a look on how this give us this important corollary, because this corollary implies the Brouwer fixed point theorem. Okay, so the proof: if there is such a map, phi, then what happened? Then we see that B, the ball, as we know, ball is single. Ball is single, and so this is B. This is a copy of B. Our map phi maps the ball B into the boundary of B, and phi left every point on the boundary unchanged. This should be B. Okay. So if we have such a map, so firstly, the ball is single. This is the first thing. The second thing, that since phi is the restriction of phi on the boundary of the ball, that is the boundary sphere, is the identity map of the boundary, because for every point on the boundary, phi x equal x. Okay, so this means phi is an identity map restricted to the boundary of B. As an identity map, if you have a parametrization of the boundary of the left ball, the composition y is exactly x itself, because phi is identity map restricting to the boundary. Okay, therefore this must be, this y is a parametrization of the boundary of B, the boundary of the right ball. This is the, if x is the parametrization of the left ball, the boundary of the left ball, then the composition of phi and x, that is our map y, is the parametrization of the boundary of the right ball. So this phi such a map phi satisfies all our requirements in this theorem. In this theorem, we require that omega is single, and the map, the only requirement for the map is firstly C2, secondly the composition which the parameterization of the boundary of omega give you a parameterization of the boundary of D. So this map, the map mentioned in the corollary, satisfies such assumption. Therefore, we can apply this theorem, the change of variable formula, for the map phi here. Okay. Now we choose a particular function. Take a particular function. Defined over the ball B, non-negative. We can take a non-negative C1 function because C1. Because our theorem requires the function, the integral function, the function to be integrated must be C1 in our this theorem. Okay, so we take a C1 function such that this function is 0 on the boundary. Such function, we have many such functions. I can even give you a precise example, but I don't want to do this because a function look -1, 1, 0. A function behave like this. Near the boundary, it is 0, and then go up. So such a function is non-negative, and it is 0 on the boundary. Okay. So we have many such functions. We don't need the explicit expression of any of the function, but we are sure there are many such functions. We take any one of these. Then this function is continuous, and not identically 0. It is positive somewhere, not identically 0. Okay. So we know that the integral of the function over the ball is positive. Because as a continuous function, so this is our function as a continuous non-negative function and not identically 0, you can prove that its integral is positive. But on the other hand, we can apply our change of variable formula. So this integral is integrating over the right ball. But the map f, we can convert this using our change of variable formula. This integral can be converted to the integral over the right ball, the left ball. For the left ball, the integral is f phi x. Then Jacobian determinant of the map, and then dx. Okay, of course we have a positive or negative sign in front of the integral, as stated in the theorem. But now let's see what happened for the integral on the right hand side. I declare that this integral is 0. This integral must be 0. Okay, so this is a contradiction. 0 strictly less than 0. Why the integral on the right hand side must be 0? So if x belongs to B, then by our assumption on our map f, phi x is belongs to the boundary. So if x is a point here, any x here, the image of x under our map phi must lies on the boundary. Okay, because this assumption. We know that phi x, sorry, not this one. This assumption, phi b contained in the boundary of B. So every point on B, on the closed ball B, is mapped to the boundary of the ball. Okay, so phi x belongs to the boundary of B, but f is 0 on the boundary, right? Our f is taken in this way. It is 0 on the boundary of the ball. So this means that f phi x is 0. For every x in B, f phi x is 0. Therefore, the integral of all phi x multiplying the Jacobian determinant, that is this function, the integral of this function must be 0, because this function is identically 0 on the ball B. Okay, so this is a contradiction. This contradiction tells us that the corollary is true. And as we show you, this implies the Brouwer fixed point theorem. Okay.